Scientists blow up gold with giant lasers, breaking decades-old physics model. Physicists unleash giant lasers on gold, unintentionally challenge a long-standing physics theory. In a groundbreaking experiment, scientists at the SLAC National Accelerator Laboratory have utilized massive lasers to heat gold to an astonishing 14 times its boiling point. For a brief moment, they feared they had shattered the laws of physics, but thankfully, that was not the case. However, they did manage to challenge a well-established model in physical chemistry that has been accepted for decades, which pertains to the fundamental characteristics of matter. In a study published today in Nature, researchers have achieved a remarkable feat. They directly measured the temperature of matter in extreme conditions for the very first time. This new method allowed them to superheat gold, pushing it beyond its boiling point into a peculiar state that exists between solid and liquid. The findings indicate that, under specific circumstances, gold may not have a limit to superheating. If this hypothesis holds true, it could open up a plethora of applications in fields such as space exploration, astrophysics, and nuclear chemistry. The research involved a two-step experimental approach. Initially, the team employed a laser to superheat a gold sample, counteracting the metal's natural inclination to expand when heated. Following this, they directed ultra-bright X-rays at the gold samples, which scattered off the surface. By analyzing the changes in the frequency of the X-rays after they collided with the gold atoms, the researchers were able to determine the speed and temperature of the atoms with precision. This experimental outcome appears to contradict a long-held theory in physics, which asserts that materials like gold cannot be heated beyond 3 times their boiling point, approximately 1948 degrees Fahrenheit, 1064 degrees Celsius. According to this theory, exceeding this temperature would lead to what is known as the entropy catastrophe, meaning the heated gold should have exploded. Surprisingly, the researchers did not anticipate surpassing this limit. Their results not only disprove the conventional theory but do so dramatically, revealing that gold can be heated to an incredible 33,740 degrees Fahrenheit, 18,726 degrees Celsius. Thomas White, the lead author of the study and a physicist at the University of Nevada, Reno, shared his astonishment during a video call with Gizmodo, recalling, "We looked at the data, and someone just said, 'Wait a minute. Is this axis correct? That's really hot, isn't it?'" It's important to note that this superheated state lasted only a few trillionths of a second and did indeed result in an explosion. However, White emphasized that this duration was still long enough to be interesting, adding, "If you could prevent it from expanding, theoretically speaking, you could heat it forever." He humorously remarked, "I'm very thankful that I get to blow stuff up with giant lasers for discoveries. And that's my job, you know." This hypothesis will require further validation through additional experiments involving both gold and other materials. Nevertheless, the superheated gold maintained its integrity long enough for the team to accurately capture its temperature using their innovative technique, as explained by Bob Nagler, a senior author of the study and staff scientist at SLAC. Nagler pointed out an interesting fact: temperature is one of the physical quantities that humans have known for the longest time, but we don't measure temperature itself. We measure something that temperature influences. For instance, a mercury thermometer gauges how temperature affects the volume of mercury. This distinction can complicate the study of real-world examples of hot, dense matter in extreme conditions, such as the core of a star, the nose cone of a spacecraft, or the interiors of a fusion reactor. Understanding the temperature, a fundamental physical property, of matter in these scenarios could significantly enhance our ability to investigate or manipulate them for practical benefits. However, these systems often rely on temperature-dependent variables that are challenging to measure. While it is theoretically possible to replicate these conditions in a laboratory, they tend to very quickly explode, Nagler noted. Moreover, one must know the actual temperature of the system being replicated to ensure the validity of the experiments. So you have a chicken and egg problem, he explained. This is why the scientists are eager to explore how their new technique can address this issue. White expressed his excitement about the implications of their work, stating, "That's the most exciting thing about this work. We now have a thermometer for all these crazy experiments we've been doing." For instance, the National Ignition Facility at the Lawrence Livermore National Laboratory employs a gold cylinder in its nuclear fusion experiments. Lasers are fired at this cylinder, causing it to emit X-rays that drive the fusion reactor. But we are also considering conducting experiments directly related to fusion now, he added. To recreate fusion conditions or the materials used in fusion reactors, and simply measure their temperature, which has actually been a long-standing question in physics. The research team is already applying their technique to other materials, such as silver and iron, and they are pleased to report that initial data has been promising. Over the coming months, the scientists will be busy analyzing what insights these metals may provide. The project is undoubtedly in full swing. *******. A previous version of this article mistakenly stated that the National Ignition Facility's nuclear fusion experiments fire X-rays directly at the gold cylinder, known as the whole round. In reality, the experiment fires lasers at the cylinder, which then emits X-rays that drive the fusion reactor. Superheating gold beyond the predicted entropy catastrophe threshold. Imagine heating gold to temperatures that should cause it to melt and collapse into chaos, but instead, it holds together far beyond what scientists thought possible. That's the startling reality we are uncovering in this study on superheating materials. What if the rules we've relied on for decades are being rewritten right before our eyes? Stick around, and you'll see how we are challenging long-held beliefs about material stability under extreme conditions. In the world of materials science, the rise of short-pulse lasers has been a game-changer, helping us skip over the messy intermediate stages that usually destabilize materials during superheating. This has paved the way for experiments that get dangerously close to what's called the entropy catastrophe threshold. Think of it as the point where everything should fall apart based on classic thermodynamics. Studies with heating rates over 10 to the power of 14 Kelvin per second have pushed gold to temperatures around 1.4 to 2.1 times its melting point, Tm, coming close but not quite hitting that critical limit. However, even with these leaps forward, we've struggled to pin down exact ion temperatures in these super-hot, dense systems without relying on indirect methods, like looking at structural changes or energy uptake. That's a big hurdle because it makes our conclusions less precise. To tackle this, our team turned to inelastic X-ray scattering in the backscattering setup, which lets us directly measure how fast the ions are moving and figure out their temperature from that. Using this cutting-edge approach, we discovered that when we hit gold with short-pulse laser beams, we can crank up the heating rate to more than 10 to the power of 15 Kelvin per second. This sends the ions soaring to about 14 times the melting temperature without the solid structure breaking down. Not only does this blow past the old predictions for the entropy catastrophe, but it also hints that the upper limit for superheating might be way higher than anyone imagined, shaking up our basic understanding of how solids behave when pushed to the brink. But here's where it gets controversial. How do we even know what temperature we are dealing with in these experiments? We relied on high-resolution inelastic X-ray scattering to get a clear read on ion temperatures in gold samples zapped by intense laser heat. When X-rays bounce off moving ions, they shift energy in a way similar to the Doppler effect you've probably heard of, like how an ambulance siren sounds higher when it's coming toward you. By analyzing this shift and the broadening of the X-ray spectrum, we can tease out the velocity distribution of the ions and calculate their temperature. In crystals, scattering from phonon modes is a tried-and-true method that, in materials like polycrystals, gives us insights into the phonon density of states. With our backscattering angle, the spectrum turns into a nice Gaussian shape, which happens when we are dealing with multiple phonons at high momentum transfers and temperatures well above the Debye temperature, around the point where atomic vibrations get really intense. For gold, the rate at which phonons equilibrate among themselves is much faster than with electrons, so we can treat the phonon system as having a single temperature, T. This Gaussian profile's full width at half maximum, or FWHM, called E_therm, links directly to the temperature through this equation. T_I equals 1K_B, asterisk, 1,4, asterisk, M_I, C², 8 asterisk ln, 2, asterisk, E_therm, E_0, caret 2. Where M_I is the ion mass, C is the speed of light, K_B is the Boltzmann constant, and E_0 is the X-ray energy. Interestingly, this formula matches what you'd expect for a classical gas following a Maxwell-Boltzmann distribution, and it doesn't depend on the specific atomic interactions or phonon details, making it pretty universal for these conditions. The energy shifts we are measuring are tiny, just about 25 millielectronvolts for gold at 1000 Kelvin, and the samples don't last long when heating rates are this extreme. So, to catch that subtle broadening, we need a super bright X-ray source and a high-resolution spectrometer. Thanks to recent upgrades at places like the Matter in Extreme Conditions instrument at the LINAC Coherent Light Source and Spectrometer Tech from the European Synchrotron Radiation Facility, we've got tools that can handle resolutions around 50 millielectronvolts and probe times as short as 40 femtoseconds. Our setup involved a 50 nanometer thick polycrystalline gold sample on a nickel grid, hit by a 45 femtosecond laser pulse at 400 nanometer wavelength. We focused the laser to a spot about 100 micrometers across, with fluences ranging from 1.9 to 4.9 joules per square centimeter. A camera outside the chamber kept track of the laser energy for each shot. The X-rays came in at 7,491.9 electronvolts, narrowed down by a monochromator, and were aimed right at the center of the laser spot. We used a spectrometer with 3 silicon analyzers to capture the scattered X-rays at angles close to 170 degrees, and a larger detector to monitor diffraction from gold's crystal planes. By adjusting the timing between the laser pulse and the X-ray probe from -1 picosecond to 6 picoseconds, around when the sample might melt, we used a time tool to precisely measure the delay between the two lasers. Because we are working with low photon counts per shot, we had to use single photon counting, converting each detected photon's energy based on the analyzer's dispersion curve and combining data from multiple shots to build a full spectrum. We figured out the instrument's function by scattering X-rays off a room temperature gold target, which gave us a spectrum that fit a Voigt profile, a mix of Gaussian and Lorentzian shapes. This helped us isolate the thermal broadening in heated samples. For instance, in one case, heating the gold led to a spectral width of 121.6 millielectronvolts, translating to an ion temperature of 19,000 Kelvin. And this is the part most people miss. While indirect methods were the norm before, our direct measurement cuts through the guesswork and could revolutionize how we study high-pressure and high-energy scenarios. Next, we tracked how the ion temperature changes over time after laser irradiation by varying the delay between the optical pump and X-ray probe. The laser kicks off ballistic electrons that heat up the thermal electrons in less than a picosecond, and any uneven heating gets smoothed out quickly due to the electron's high thermal conductivity. Then, energy transfers to the lattice through electron-phonon interactions, with the electrons acting like a heat bank. We didn't need to model this transfer because our method measures the ion temperature directly. To keep things consistent, we measured key parameters like laser fluence and pulse delays for each shot, grouping data into low and high fluence categories. For the lower fluence around 1.9 joules per square centimeter, we hit a heating rate of about 3.5 times 10 to the power of 15 Kelvin per second, and for the higher one at 4.9 joules per square centimeter, it was around 6 times 10 to the power of 15 Kelvin per second. Using a wide-angle X-ray detector, we saw the Debye-Scherrer rings from gold's 111 and 200 planes fade over time, which tells us when melting occurs. As atoms jiggle more with rising temperature, the ring intensity drops, following the Debye-Waller effect, kind of like how increased vibrations blur a picture. At the slower heating rate, we got the gold up to 13,800 Kelvin, or about 10 times Tm, and at the faster rate, to 19,000 Kelvin, roughly 14 times Tm. In both cases, we stayed solid well above the proposed 3 times melting temperature limit for over 2 picoseconds, which is plenty of time for melting to happen if conditions were right. This challenges the idea that materials can't handle such extremes without breaking down. Now, let's dive into the discussion. The entropy catastrophe prediction stems from thermodynamics, saying that a liquid's entropy can't dip below a solid's at the same enthalpy, or you'd violate fundamental laws. Back in the day, plotting entropy curves suggested critical points where things go haywire, like the Korsman temperature for glass transitions and the higher entropy catastrophe temperature around 3 Tm, where melting should kick in abruptly. For gold, calculations based on heat capacities showed this crossing at about 3 Tm. But our results show temperatures way beyond that, which shouldn't be possible if we follow the standard model. To make sense of this, we realized that in our ultra-fast experiments, the lattice doesn't expand or ablate much within the short timescales, as confirmed by stable Bragg peaks and other studies. Without expansion, the entropy contributions from thermal effects and electrons stay low, so the solid's entropy doesn't cross the liquid's, allowing superheating to go further. Essentially, by heating so quickly, we are sidestepping the catastrophe. And this is the part most people miss. If heating is fast enough to prevent expansion, maybe there's no real upper limit to superheating. Superheated gold challenges physics. New method reveals extreme temperatures. In a groundbreaking discovery, researchers have challenged established physics by directly measuring the temperature of atoms in superheated materials, disproving a long-held theory and pushing the boundaries of our understanding. The team's findings, published in the prestigious journal Nature, https://www.nature.com/articles/s41586-025-09253-y, reveal that superheated gold can withstand the so-called entropy catastrophe, an event that was previously believed to mark the ultimate limit for superheated materials. Measuring the temperature of extremely hot substances, known as warm dense matter, has been a significant challenge for scientists. These materials, found in extreme environments such as the cores of planets or fusion reactors, can reach temperatures of hundreds of thousands of degrees Kelvin. Accurate temperature readings are essential for comprehending complex systems, but until recently, obtaining these measurements was nearly impossible. We have reliable methods for determining the density and pressure of these systems, but not their temperature, explains Bob Nagler, a staff scientist at the Department of Energy's SLAC National Accelerator Laboratory. Estimating temperatures has always come with large uncertainties, hindering the development of our theoretical models. This has been a persistent issue for decades. However, the latest research offers a solution to this long-standing problem. A team of international researchers, led by Tom White, an associate professor of physics at the University of Nevada, Reno, and colleagues from institutions such as Queen's University Belfast, the European XFEL, Columbia University, Princeton University, the University of Oxford, the University of California, Merced, and the University of Warwick, Coventry, have developed a novel method to measure the temperature of atoms in warm dense matter. Unlike previous approaches that relied on complex models, this new technique directly measures the speed of atoms, providing a clear indication of the system's temperature. In a remarkable experiment, the researchers superheated solid gold to temperatures far exceeding the theoretical limit, effectively overturning 4 decades of established theory. By using a laser to heat a nanometer-thin sample of gold and then sending a pulse of ultra-bright X-rays through the superheated material, the team observed the X-rays scattering off the vibrating atoms. This interaction caused a slight shift in the frequency of the X-rays, allowing the researchers to determine the speed of the atoms and, consequently, their temperature. Our direct measurement technique opens up new possibilities in the field of laser-heated matter research, says Siegfried Glenzer, director of the High Energy Density Science Division at SLAC and co-author of the paper. Combined with the capabilities of the LINAC Coherent Light Source, LCLS, This method plays a vital role in advancing high-energy density science and its potential applications, including inertial fusion. The team was initially focused on demonstrating the effectiveness of their temperature measurement technique, but upon analyzing the data, they stumbled upon an unexpected revelation. They discovered that the superheated gold reached temperatures as high as 19,000 kelvins, 33,740 degrees Fahrenheit, over 14 times its melting point, without undergoing the anticipated entropy catastrophe. This finding defied the long-standing theory from the 1980s, which posited that materials would inevitably experience a catastrophic transition to a different phase as they exceeded their normal melting and boiling points. We didn't set out to disprove this theory, but that's the beauty of science. You never know what you might uncover, remarks White. It's crucial to note that the researchers did not violate the second law of thermodynamics. Rather, they demonstrated that the entropy catastrophe can be avoided under certain conditions. In this case, the rapid heating of the gold prevented it from expanding, allowing it to maintain its solid crystalline structure. The implications of this discovery extend beyond the realm of physics. Researchers studying warm dense matter for fusion power plants and fusion fuel targets, as well as observing fusion reactions at the atomic level, stand to benefit from this new method. With the ability to directly measure atom temperatures ranging from 1,000 to 500,000 kelvins, scientists can gain valuable insights into the behavior of materials under extreme conditions. Nagler envisions numerous applications for this technique, including the study of materials shock compressed to mimic the conditions deep inside planets. He is particularly excited about its potential impact on inertial fusion energy research at SLAC. Understanding the temperatures at which fusion fuel targets undergo critical state changes is crucial for designing effective targets, he explains. Now, we have a means to make those measurements accurately. This revolutionary discovery not only challenges established physics but also opens the door to further exploration. The team's success in measuring temperatures in superheated materials hints at the possibility of even more profound revelations waiting to be uncovered.